Imagine a giant wall of concrete holding back billions of liters of water. Behind that wall, water is storing enormous amounts of potential energy. But how can simple water produce electricity for millions of homes? And what happens when a power grid needs electricity suddenly, especially at night or during peak demand? The answer lies in one of the oldest and most powerful forms of renewable energy, hydropower. Today, we are going inside a hydroelectric power plant and a pumped storage power plant to understand exactly how they work, step by step. Hydroelectric power is electricity generated using the energy of moving water. The basic idea is surprisingly simple. Water is stored at a higher elevation. Because of gravity, that water has potential energy. When the water is released and allowed to flow downhill, its potential energy is converted into kinetic energy. That moving water is then directed toward a turbine. The turbine spins. The turbine is connected to a generator, and the generator converts mechanical energy into electrical energy. That electricity is then sent through transformers and transmission lines to homes, factories, businesses, and cities. So the basic chain is stored water, moving water, turbine, generator, electricity. A typical hydroelectric plant has several important components. The first is a reservoir. The reservoir is the large body of water stored behind the dam. The second major component is the dam. The dam holds back the water and creates a difference in elevation, known as head. The greater the available water flow in head, the greater the potential electricity generation. Next comes the intake structure. This is where water enters the power plant system. Gates can control how much water enters. From the intake, water travels through a large pipe or tunnel called a penstock. The penstock carries water toward the turbine under high pressure, and this is where the real transformation begins. 3. How the turbine produces mechanical energy. As water rushes to the penstock, it reaches the turbine. There are different types of turbines used in hydropower plants. For example, Francis turbines are commonly used for medium head applications. Pelton turbines are suitable for high head locations. And Kaplan turbines are often used where there is high water flow and relatively low head. Regardless of the design, the principle is similar. The force of the water pushes the turbine blades. The blades rotate. That rotation turns a shaft connected to the generator. So the turbine converts the energy of moving water into mechanical rotational energy. But we still don't have electricity yet. That happens inside the generator. 4. How the generator creates electricity. Inside the generator are powerful magnets and coils of conductive wire. When the turbine rotates the generator shaft, the magnetic field moves relative to the coils. This movement produces an electric current through electromagnetic induction. In simple words, the turbine spins the generator, and the generator produces electricity. The electricity generated at the plant is then sent to a transformer. The transformer increases the voltage so electricity can travel efficiently over long distances. High voltage transmission lines then carry that electricity towards cities and industrial areas. Finally, substations reduce the voltage to safer levels before electricity reaches homes and businesses. After passing to the turbine, the water isn't destroyed. It simply continues downstream. The water exits through a channel called the tail race and returns to the river. This is one of the major advantages of conventional hydropower. The water acts as the energy carrier, while the flow itself can continue through the natural river system. During periods of heavy rainfall or when the reservoir becomes too full, excess water may need to bypass the turbines. This is where the spillway becomes important. The spillway safely releases excess water downstream and helps protect the dam. 6. But what is pumped storage hydropower? Now let's look at something even more interesting. A conventional hydroelectric plant generates electricity when water flows downhill. A pumped storage power plant can work in both directions. It can generate electricity, and it can also store electricity. This makes pumped storage one of the most important technologies for balancing modern power grids. Think of it as a giant rechargeable battery, but instead of storing energy inside chemicals, it stores energy by moving water uphill. Imagine a city during the middle of the night. Most people are sleeping. Electricity demand is relatively low, but power stations and renewable energy systems may still be producing electricity. instead of allowing some of that energy to go unused. A pumped storage plant can use the electricity to pump water uphill. Then imagine the next afternoon. Millions of people return home. Air conditioners turn on. Factories are operating. Electricity demand suddenly rises. The pumped storage plant can release the stored water downhill and quickly generate electricity. This makes pumped storage extremely useful for handling peak demand. 9. Pumped storage and renewable energy. Pumped storage becomes even more important when we look at solar and wind power. Solar panels produce electricity, mainly when the sun is shining, but electricity demand doesn't always match solar production. For example, solar generation can be high during the afternoon, while electricity demand may become even higher in the evening. Pumped storage can help solve this timing problem. During periods of high renewable generation, excess electricity can be used to pump water uphill. Later, when electricity is needed, the stored water is released to generate power. Wind energy has a similar challenge. Wind speeds can change throughout the day. Pumped storage can help absorb some of these fluctuations and provide electricity when renewable generation falls. As electricity systems become increasingly dependent on solar and wind energy, energy storage is becoming more important. Batteries are one solution, but pumped storage offers another solution at very large scale. It can store enormous quantities of energy and release that energy when the grid needs it. This is why many energy experts consider pumped storage an important part of future electricity systems. The technology itself is not new, but its role is becoming increasingly important as the world moves toward cleaner electricity. Final conclusion. So, how does a hydroelectric power plant work? It starts with water stored at a higher elevation. Gravity pulls that water downhill. The moving water spins a turbine. The turbine drives a generator. The generator produces electricity, and the electricity travels through transformers and transmission lines to the grid. A pumped storage plant takes the same basic idea and adds something remarkable. It can take electricity when demand is low